Thanks, Ben, and thanks for inviting me here. So I want to describe some work in progress joined with Artem Kalmykov. The big goal is to better understand quantum groups, and in particular dynamical quantum groups. And some motivating questions for this particular project that I will get to in the talk are the following. So the first question is, what is the categorical meaning of a dynamical R-matrix? I will say later what such an object is, but for those of you who know something about R-matrices, one way to interpret categorically an R-matrix for a quantum group is that you have a braid monoidal category, C, and it has a monoidal functor to the category vector spaces. So this is not a braided monoidal functor, it's monoidal functor. And then you can, since it's not braided, you can measure how non-braided this functor is. So for any two objects of C, you can braid them, look at the image under F, and then braid them in the vect. So this measure, well, it's going to be an endomorphism or even an automorphism of tensor-product of two objects of C. And this is going to satisfy the Yang-Baxter equation. So this is an R-matrix. This is one way to interpret what an R-matrix is categorically. There's also a class of so-called dynamical R-matrices. So what I've described just now are called constant R-matrices, or just a matrix. While dynamical R-matrices are things that depend on parameters on the Cartan subalgebra of the quantum group. So the question is, is there a similar categorical point of view on dynamical R-matrices? All right, so that is the first motivation. Another motivation is the following. It's slightly imprecise, but the idea is, okay, so suppose you have some simple Lie algebra G, and H is the Cartan subalgebra. Then you have this Harish-Chandra homomorphism from the center of the universal enveloping algebra of G to the symmetric algebra on the Cartan. And there's a famous Harish-Chandra isomorphism between the center of the universal enveloping algebra of G and W invariance, the wild group invariance of sim H. Is there some categorical, is there something categorical that happens that implies this Harish-Chandra isomorphism? Okay, I will be a little bit vague what I mean by categorification. Just now, you'll see in a few slides a more precise statement. And finally, another motivation is there's a procedure to start with a Hamiltonian G space, where G is again some, let's say, finite dimensional complex simple group, and turn to the Hamiltonian space for the Cartan. So this is called symplectic implosion. And the question is, what is the quantization of such a procedure? Okay. So let me begin with just saying a few words about Hamiltonian reduction, because I want to get to symplectic implosion. And I want to phrase this in a slightly new way for some of you, but it's going to be related to shifted symplectic structures that we've heard about in Tristan's talk and in Sarah's talk. Okay, so suppose you have a smooth variety with a Hamiltonian G action. So that means that you have a symplectic variety, you have a G action on that symplectic variety, and you have a moment map from X to the Lie algebra dual, which is G equivariant in particular, and it satisfies some equation, the so-called moment map equation. So since this map is equivariant, you can mod out this map by G, and you get an induced map and quotients. So you have a map from X mod G to Lie algebra dual mod G. Now you start with X being a symplectic variety, so you can ask what are symplectic properties of this map, or objects appearing in this map. One thing you're going to observe is the target G dual mod G. You can write it somewhat funnily. you can write this as a shifted cotangent bundle of BG. So you can think about the Lie algebra dual as being the cotangent direction. And so the cotangent complex of BG is G dual in degree +1. So that means that this object has a natural one-shifted symplectic structure in the sense of Pontiff-Toine Vaquevitz-Ozzy, just like you have a symplectic structure in a cotangent bundle. Okay, and all right, so this is what we have in the target. And now what about this map? And then there's this nice theorem of Kalak that says that a one-shifted Lagrangian structure on this map mu is the same as the data of a symplectic structure on X, which makes mu into a moment map. So again, the Lagrangian is in the sense of Pontiff-Toine Vaquevitz-Ozzy, so it's not necessarily an embedded Lagrangian, it's a derived Lagrangian. Okay, and conversely, you can interpret things like Hamiltonian reduction in this way. So if you start with such a Lagrangian inside of G dual mod G, well, one thing you can do is you can look at the intersections with some other Lagrangians. So for instance, there's a easy Lagrangian G dual inside of G dual mod G. And if you do this intersection, you get something symplectic, and this is the original variety. Another natural Lagrangian is BG in G dual mod G. And if you do that intersection, then you just get Hamiltonian reduction. Okay, so the upshot is that if you have a Lagrangian inside of G dual mod G, you can do some Lagrangian intersections. There are two natural ones. One of them returns the original variety. The other one gives you Hamiltonian reduction. Okay, so let me explain deformation quantization of this picture. And before I say that, I have to say what I mean by deformation quantization in this shifted symplectic context. So if you start with a symplectic variety, usually deformation quantization means something like start with the algebra of functions, which is a commutative algebra, and then write down some star products, so deform it to an associative algebra. Or alternatively, maybe your variety is not affine. Something better is to look at the category of sheaves, which is a symmetric monoidal category, and to deform it to a category which has no monoidal structure anymore. What happens in this one-shifted context is that you can again talk about deformation quantization, except now you start with a symmetric monoidal category, quasi-granular sheaves on that variety, and you can deform it to a monoidal category. So that's what differential quantization is in this context. All right, so I had a one-shifted symplectic variety, which is G dual mod G. So let's try to look at the differential quantization of this space. Okay, so quasi-granular sheaves on G dual mod G, there are G-covariant sheaves on the Lie algebra dual, and sheaves on Lie algebra dual are the same as modules for the symmetric algebra. So quasi-granular sheaves are modules on the symmetric algebra equipped with the compatible action of the group G. And it's kind of easy to imagine quantization of this picture. You just replace sim G by the universal developing algebra, UG. So the quantization is what's called the category of Harish-Chandra bimodules. One way to think about this is it's the category of UG modules internal to the category of G representations, where G is the group. Another way to think about this is, so there's the word bimodule in the name. You can think about these as UG bimodules, where if you look at the diagonal action, it integrates to the group. Okay, so this is the category of Harish-Chandra bimodules. Because these are bimodules, there's a natural monoidal structure, just relative tensor of bimodules. Okay, let me give an easy example, which will be relevant for dynamical R-matrices, which is the case that the group is abelian. So you just have a torus. Let's say H is a torus, and then with some character lattice lambda, then this category of Harish-Chandra bimodules, well, it's just going to be the category of lambda graded sheaves on Lie algebra dual. as a plane category. So as a plane category, it's the same as the classical one. The tensor product is slightly different. So here's a formula. So basically, you decompose, so you have two modules, M and N. You decompose them into the weight spaces, M of lambda and N of lambda. And then the tensor product basically shifts the first module by lambda, where lambda is the weight of the second module. So if you have N of lambda, which is concentrated purely in weight lambda, then the tensor product means you shift the first module M by lambda. So you just have translations on the Lie algebra dual, and then use the usual tensor product in quasi-continuous sheaves. Okay, so it involves some kind of shift. And this is a shift that will be relevant for dynamical R-matrices later. Okay, so now let me, so far I explained quantization, differential quantization of Lie algebra dual mod G. Let me also explain what is deformation quantization of the rest of this data. So you have Lagrangian and you have these two intersections. Okay, so for this I have to remind you something basic, which is the notion of a quantum moment map. So if you have an algebra with an action of a group G, then a quantum moment map is basically the data that tells you that the Lie algebra action on the algebra is inner. So again, in formulas, this means that if you have some element of the Lie algebra and you act by it on the algebra, then you get some derivation, and the claims that this derivation is inner. And so it's just given by commutator with the value of the moment map on that element. And there's a fairly straightforward interpretation of quantum moment maps in terms of Harish-Chandra bimodules. So probably what everything here doesn't deserve to be called a proposition. But there are related results that are proven by Benzi, Jordan, and myself. So if you look at an algebra in the category of Harish-Chandra bimodules, well, as an object, it's going to be something equivalent to the G action. So it's going to be a G equivalent algebra together with a quantum moment map. Okay, so this is how we can say this for algebras. But you can also say this for categories. So what is a notional quantum moment map for categories? Well, suppose you have a G action on a category. So by this, I mean a weak G action. So action of quasi-continuous sheaves on the group G. Then one way to say the data of a quantum moment map is to say that this is promoted to a strong action. So the action of D modules on the group. Another way, which is equivalent, is to say that you take G invariance on the category, and this G invariant category is a module category for Harish-Chandra bimodules. And then you can write a quantum version of this Lagrange intersection I've shown you before. So if you want to recover the original category, well, you take this module over Harish-Chandra bimodules, C upper G, so G invariance on C, and then you just tensor this with UG modules, which is another Harish-Chandra of G module category. So then you just get the original category C. So Ben is asking what I mean by C upper G. C upper G means G invariance on C. So you have a G action on C, and you look at G invariant objects on C. And another thing you can do is to do quantum Hamiltonian reduction, which is take this invariant category and tensor it with another HCG module category, which is Rep G. If you take this relative tensor product, you get quantum Hamiltonian reduction. Okay. So
we got quite a few questions showing up. You might want to go back to that previous slide.
Yep.
Wait, let me just unmute some people.
So what are the morphisms? So the objects in C over G are the objects which are isomorphic to G twists?
Well, you have to say this in a categorical way. So you would say this. So let me, for simplicity,
Okay,
say
so equivariant objects?
Yeah. Yeah, so this is just the equivariant category. So
okay, okay, fine. That's okay.
Finite groups, it is just objects together with an isomorphism to its list.
Yeah, okay, thank you.
Is it possible to get the whole of the Harish-Chandra category as a deformation quantization of some one-shifted symplectic object, as opposed to just this diagonally?
But it is the whole. So it is the whole category that is the quantization of G dual mod G.
Oh, sorry. So I actually meant the bimodule category, the larger category.
Just the bimodule category. I think in a silly way, you can replace the group G by the formal group. Then you can get the same, just UG bimodules without integrability. All right. So let me say a few words about this procedure of symplectic implosion. Let's start with the complex semisimple group G, and let's choose a Borel and maximal torus, B and H. So there's a procedure called symplectic implosion, which, as I said, takes a G Hamiltonian space and spits out an H Hamiltonian space. So in the case of compactly groups, this was defined in, I think, 2000 by Gilman, Jeffrey, Shamar, and somewhat more recently for either actions of complex Lie groups on holomorphic symplectic varieties or compact Lie groups on hyperkähler varieties. It was defined by Dancer, Kerwin, and Swan. And I will be talking about the later version. So I'll be talking about complex semisimple groups. And so I will not say what it is exactly, because the definition is somewhat involved. If you do it with ordinary symplectic varieties, usually you get some stratified symplectic space. But if you want to work with derived symplectic spaces, then it has a very easy interpretation. So let's look at this correspondence. So you start with the Lie algebra of the Borel B mod the group Borel B, so a joint quotient, and you can map it either to the dual of the Cartan mod, the group Cartan, or the dual of the Lie algebra G mod, the group G. So this is going to be a Lagrangian correspondence in the sense of, again, shifted symplectic structures. So G dual mod G is one shifted symplectic, H dual mod H is also one shifted symplectic, and then B mod B is Lagrangian in the product of the two. Okay, so now, yeah.
Sorry, just can you comment on why you want B and not B dual?
So there is another thing, which is B dual mod B. So B dual mod B is one shifted symplectic. This is something, and B dual doesn't map to G dual, for instance. B dual receives a map from G dual. This is another thing which is a Lagrangian. So B mod B doesn't have any symplectic structure. It has a Poisson structure instead. You'll see also in a second the more classical description of this middle guy. All right. So okay, so this is a natural one-shifted Lagrangian correspondence. So what can you do with Lagrangian correspondences? You can compose them. So suppose you have a Hamiltonian space, which, as I said, is a Lagrangian in the guy on the left. So it's in Lagrangian in G dual mod G. Then you can think about this Lagrangian correspondence as giving you an integral transform. So you can think about B mod B as being the integral kernel, and then you essentially do something like pull push. if you do this composition, you end up with a Lagrangian inside of H dual mod H. And again, by the same theorem, Lagrangian H dual mod H is an H Hamiltonian space. And the theorem is that this is symplectic implosion. So in other words, symplectic implosion is just a kind of parabolic restriction or parabolic induction in the land of symplectic varieties. All right. So let's look at this correspondence again. So I want to say this in a slightly more classical way without writing these complicated stacks. So one way to think about.
Sorry to interrupt. Have you told us what the maps are? Can you maybe tell us what these maps are from B mod B to these two things?
Yeah. So you have a natural map from B. So first of all, there's a natural isomorphism between B and G mod B, G mod N. So that gives you a natural map to, let's see, so G maps to G mod N. So this gives you a natural map to G dual, and then there are different ways to write the other map, but you have a natural projection from B to H, and then you can identify with H dual, or you can write it without the choice of the killing form as well.
Thanks.
All right, so you have this Lagrangian correspondence. So let me say this a little bit more classically. So here's how you can think about the middle guy, B mod B. You just take the cotangent space of the base affine space, so of G mod N. The base affine space has a left action of G and a right action of the cartan H. Then you take this cotangent bundle and you mod out by G on the left and H on the right. So here I'm not taking Hamiltonian reduction, I'm just taking just ordinary quotient by G and H. And the claim is that this is just B mod B. Okay, now let me say some interpretation of these maps given this isomorphism. So if you look at the map on the left is a version of the Gortnik-Springer resolution. So one way to think about that is you look at, again, cotangent bundle of the base affine space, mod out by H. You have a Hamiltonian action of G. On the left, you have a moment map into G dual, and that's the Gortnik-Springer resolution. You can also think about the H action on the right of the cotangent bundle of the base affine space, and you can look at the moment map for that. Or you can think about a family of twisted cotangent bundles of the flag variety. And they're parameterized by weights in H dual. So that's the interpretation of the two maps. So one map is the Gortnik-Springer resolution, the other map, it's a family of twisted cotangent bundle. And an important fact that I will mention again later in a quantum level is that if you look at a map on the right and you restrict to an open subset of regular weights, so if you look at this map generically, then this map is an isomorphism.
Quick question, Pavel. In the second bullet point, are you supposed to mod out by G instead of modding out by H that time?
I don't think so. So
no?
if you take cotangent bundle of G mod N and you look at Hamiltonian reduction by H, then you just get cotangent bundle of the flag variety.
Mm-hmm.
And here I'm taking not Hamiltonian reduction, but just bonding out by H without setting the moment map value to be something. So that's the universal family of twisted cotangent bundle.
Okay. All right, cool, thank you.
All right. All right, so I think it's time for the break. put up some slides.
Great. That's what I was just about to suggest. So we will allow participants to unmute themselves so people can ask more questions. And I think my interpretation of Ben's question from the last slide is you're mapping down to a quotient by age. So don't you want, like on the image of that map, you haven't quotiented by age in that second bullet point. So why did you quotient by age in the first part?
It's just to have a name. There's already a thing called logarithmic spectral resolution, which is a resolution of which is thinking that maps to G-dual.
No, but I mean the second bullet point.
And the second bullet point is just to have, again, so
It's not a moment map, though, right?
it is the moment. It's exactly the moment map. So this has a map to H dual, but it also has a map to G mod B. And so if you look at this map to G mod B, this realizes this quotient as a family of twisted potential bundles. The family is parameterized by setting the moment map value for H.
Okay.
In your second bullet point on this quantum page, no, you're on the right page. Are there any assumptions you need on the DG category C to have like CG times over the Harish-Chandra category of UG modules to be C?
You don't need any assumptions on C. You need assumptions on G.
I guess what I'm thinking is that aren't there categories C for which the strong invariants are 0? And then this seems like it would kill the whole left-hand side.
Sorry, I'm not taking strong invariance. C upper G means weak invariance.
Ah, thank you.
Yeah, strong invariance is the second, is the Hamilton reduction.
And would sort of part of this work for an arbitrary affine algebraic group G?
No. What I've written here. So for this, you need, of course, a split. So here I'm talking about the torus.
Yeah. But there are parts of it where there is no torus. So there's stuff with bimodules and so on.
Yeah. So in that case, it works for any affine algebraic group. When you talk about Harish-Chandra bimodules, of course, if you want an embedding, you want probably connected. But yeah, the same assumptions.
Yeah.
And also assume that the diagram works also for the parabolic. And you replace the
with this B modulo B, you are somehow thinning by using the killing form.
Yeah.
So I mean, a natural thing should sort of a canonical thing should be without killing form in a way.
Yeah, you can write this without the killing form. Then what I call B is so B is by definition the kernel of G dual to N dual.
Yeah.
And
okay.
that doesn't. If you define it in that way, then it doesn't.
Aha. Okay. Thanks.
So in this picture here, you can replace the Borel by parabolic, and then replace
exactly.
by the Levy subgroup. Everything should be working.
Yeah. So there are two generalizations that I will actually. Well, I'll mention one generalization, but not the other one. Yeah. So the one generalization is you can replace this by any parabolic and the Levy. This is still Lagrangian. Yeah, and in the land of symplectic varieties, this is called a partial symplectic implosion.
Should we resume the talk?
I was about to suggest the same thing.
All right. So, okay. So I've described the symplectic implosion, which is a procedure for symplectic varieties. Now I want to explain the quantization of that. As you saw, things like G dual mod G are related to Harish-Chandra bimodules. So quantization of that will be will give you some functors on the category of Harish-Chandra bimodules. So this is the parabolic restriction and induction functors. All right. So let's try to quantize that. So as I said, G dual mod G quantizes to a monoidal category, which is the category Harish-Chandra bimodules for G. H dual mod H quantizes to another monoidal category, which is the Harish-Chandra category, the category of Harish-Chandra bimodules for the torus. Now, if you're, there are many ways to write this B mod B, but if you think about it, one way to write this is as G dual Hamiltonian reduction by N, and then ordinary quotient by H. So if you just look at G dual, she's in that deformed to UG modules. If you look at Hamiltonian reduction G dual mod N, that means you look at UG modules where N acts locally nilpotently. And then further quotient by H just means you have an additional action of the group H. Okay, so this is what's written in the middle. This is this category of highest weight modules for UG, equipped with an extra action of the torus H. Now, at the top, I had a Lagrangian correspondence, and the things on the outside quantize to monoidal categories. So the thing in the middle will quantize to a bimodule category over the two. Now, in this presentation, it might be difficult to see why this is a bimodule category, but there's yet another way to write this middle guy. So you can write this this category as UG-UH bimodules, where if you look at the diagonal Borel action, it's integrable. Now, just because you have UH modules, you can act by UH bimodules on one side, and on the other side you have a UG module, so you can act by UG bimodule on the other side. So this is some kind of version of category O where you have an additional H action, essentially. All right, so so this is the bimodule. Let me try to extract some functors out of that. Okay, so this bimodule category has a canonical object. This canonical object is the quantization of the structure sheaf of B mod B. So the structure sheaf quantizes to an object of this category of UG-UH bimodules with the integrable B action, which is the universal Verma module. So it's it's UH induced to UG via the Borel. Okay, so now you have, now once you have an object, you have canonical functors, not just an action, you have a functor from these categories, which is given by action on the canonical object. So what you can do is you can take in, so these functors are colimit preserving. So they will automatically have right adjoints. So you can take adjoint on the other side, and what this gives you is either parabolic restriction, which means you read this diagram from right to left, or parabolic induction, restriction is reading it from left to right, and parabolic induction is reading from right to left. Okay, so more explicitly, if you start with a Harish-Chandra bimodule for G, so it's some UG bimodule, you tensor it with the universal Wurm module and look at the highest weight vectors. So this is parabolic restriction, and parabolic reduction is doing the opposite. You start with an UH bimodule, tensor this with the universal Wurm module. This will have an action of, so I wrote P, here I meant B. So you start with some, you have an integrable action of B, and then you can look at the co-induction from B to G. Maybe a little bit more explicitly, you can write this as sections of flag variety of some module. So this module is the following. You can take differential operators on the base affine space, which are monodromic for the carton for H. And then you push them forward to G mod B, to the flag variety. You still have the monodromic parameter, so this gives you a UH action on this algebra. Then you can look at the tensor product with that UH bimodule Y. Now, UH bimodule Y, well, it had an integrable H action, so you can look at the corresponding vector bundle of the flag variety. This is what I mean by Y underlined. And this is what the induction functor is. Let me say that neither of these functors are colimit preserving, so that they're not, neither left nor right exact. Okay, but let me talk about some monoidal properties of these functors. Okay, so one fact is that if you have this situation, you have a bimodule category over two monoidal categories, and you have a canonical object in the bimodule category, and then you do this game with taking the action, taking the adjoint. Then by abstract nonsense, the corresponding functor will be lax monoidal. There's something special about parabolic restriction, is that if you apply this to the unit of the category Harish-Chandra bimodules, which is UG, you actually get the unit of Harish-Chandra bimodules for H. So I said it's lax monoidal. A priori, there's a map from UH into parabolic restriction, into this parabolic restriction of UG, and the claim is that this is an isomorphism. This is not true for the tensor structure, so it's honestly a lax monoidal functor. Now, since it's a lax monoidal functor, it sends algebras to algebras. So if you have an algebra in Harish-Chandra bimodules for H, it gives you an algebra in Harish-Chandra bimodules for H. Sorry, for G, it gives you an algebra in Harish-Chandra bimodules for H. And I mentioned before that algebras in Harish-Chandra bimodules are the same as algebras with a quantum moment map. So this is the quantization of symplectic implosion. So you have an algebra with a G action and a quantum moment map for G, which gives you an algebra object in Harish-Chandra bimodules. You apply parabolic restriction length in Harish-Chandra bimodules for H. So this gives you an algebra with an H action and a quantum mode map for H. Another thing is that, okay, I said that you have a map on units, which is an isomorphism. So you can look at the endomorphisms of units. And you can see what this gives you. This map on endomorphisms of units is just the Harish-Chandra homomorphism from the center of the universal enveloping algebra to symmetric algebra on the Lie algebra H. Okay, so you can also talk about the other functor, parabolic induction. It will not be relevant for what I'm about to say about dynamical R-matrices, but let me just briefly say that a few properties is that just as restriction, it's also lax monoidal, but it's honestly lax monoidal. So on the unit, it's also not going to give you the unit. So if you take the unit in Harish-Chandra bimodules for H, that's UH, you induce it to Harish-Chandra bimodules for G, you don't get UG, but you get W many copies of UG. So it's UG tensors over the center of UG with UH. All right, so I said that this functor is Lax monoidal. Now I will need actually a monoidal functor, so let me explain how to get that. So you can look at the, so as I said, Harish-Chandra bimodules for H, there's some kind of sheaves on the dual of the Lie algebra H together with an action of the carton.
Pavel, I had a quick question.
Yep.
Is there like a Val group action on the fibers of the restriction functor at all?
There will be in a few slides. Yeah.
Oh, okay. Sorry. Thanks.
Yep. Right. So you can look at, so you can replace module for the symmetric algebra by some rational version. Basically, you throw away all integral weights. So sheaves on H dual minus integral weights. Well, and now again, you can look at this module category over Harish-Chandra bimodules for H. And if you do this localization, so you throw away integral weights, what this becomes is a free rank 1 module. So what this means is that the action functor from Harish-Chandra bimodules for H on this module category, where you act on this universal Voron module, is an equivalence. And a corollary is that if you look at this parabolic restriction functor, it's actually not just lax monoidal, it's strongly monoidal generically. And it's also exact. The idea of this proof is kind of interesting. It involves something that seems to be quite classical, but I haven't encountered this before. It's this notion of an extremal projector. So it was introduced in, I think, 70s and 80s by Sharova, Smirov, and Tolstoy, and Zholobenko. So it's basically an element of some completion of UG. So it's both completion and localization of UG, which is an idempotent. So it squares to itself. And it satisfies this finding property that if you multiply by E alpha on the left or by F alpha on the right, just get 0. So if you have any UG module where this element actually makes sense, then what it's going to do is it's going to project to the highest weight subspace. That's why it's called an extremal projector.
Pavel, don't you need to remove more than just integral weights here? Like basically kind of category O for generic weight in a different sense has the shape you're saying, but like it's something like you have to pair with every root to have something non-integer.
Yeah. Right. You're right. Thanks. Okay. Right. Yeah. So the condition is really, yeah. As Sam said, the condition is that this is not an integer. All right. So okay. So what's the meaning of this external projector? You have so I already explained that you have this functor from the Harish-Chandra category of Harish-Chandra bimodules for H to this category of UG-UH bimodules with an integrable action of B. So you have an bimodule X, and you send it to the tensor product of the universal Voron module with X over UH. And then you can also write an inverse functor, which is you take bimodule y, and then you send it to the universal Verma module for the opposite parabolic, sorry, for the opposite Borel. Then you get an UH bimodule. The claim is that if you start in Harish-Chandra category Harish-Chandra bimodules for H, go to this version category O back to Harish-Chandra bimodules for H, that's just equal to the identity. But if you do the other way, it's not going to be isomorphic to the identity. But if you work generically, you can write such an isomorphism. And such an isomorphism is exactly given by applying this extremal projector. All right. So, right. So let me give another fact that I will need for dynamical R-matrices. Okay, so there's a natural functor from representations of the group G to Harish-Chandra bimodules, which is constructed free Harish-Chandra bimodule. So if you have representation V, you send it to UG tensor V with a free left UG action, and the right action is given by combination of the G action on UG and on V. Now, in general, if you start with a free Harish-Chandra bimodule and you do parabolic restriction, you will not get something free in H, but it claims that you actually get something free generically. And again, the proof of this fact uses an external projector. So the construction of this natural isomorphism involves an external projector. That's maybe one of the reasons you might think that the generic should appear. All right. So I said the motivation was to understand something about dynamical R-matrices. So let me say where they appear. Okay, let me begin with the story that I already mentioned. You have a braided monoidal category, C, and a monoidal functor into vect. Then you can measure how this functor F fails to be braided. So you can construct this automorphism R. And then this automorphism R, which is the difference between the braidings on C and on vect, is going to satisfy the Yang-Baxter equation. So if you have 3 objects X, Y, and Z, then you can act by R 3 times. So basically, R23 means you act on Y and Z, and you don't do anything with the X. R13 means act on X and Z, don't do anything with the Y, and then R12 means act on f of X and f of Y, don't do anything with the Z. Okay, and this is just, yeah, this follows from naturality and the hexagon axioms. Okay, so this is one way to encode an R matrix categorically. You have a braid monoidal category and you have a forgetful functor into vect, which is just monoidal. And here's how you can encode a dynamical R matrix. So suppose you still have a braid monoidal category C, but it has a functor not into, it has monoidal functor not into vect, but into the category Harish-Chandra bimodules. And I will also assume that actually this monoidal functor lands in the subcategory of free Harish-Chandra bimodules for H. If you play more or less the same game, so kind of measure how the braiding on C differs from the natural braiding on the vect, you can construct a dynamical R matrix. So you start with an object X of C, then you can extract an H representation by applying this functor G. And then you have some automorphism, which is now going to depend on the element of the carton. And if you similarly just work out what the hexagon and naturality axioms give you, what it implies is the so-called dynamical Yang-Baxter equation. So this, so here the indices mean the same thing as I said above. So that means you act on X and Y, X and Z, and Y and Z separately. And then this H1 means the following: G of X, G of Y, and G of Z are H representations. So H upper 1 means extract the weight of the vector you have in slot X, or in the first slot. So you shift the dynamical parameter by the weight on the X slot. And this is, the proof of this is very, follows pretty much immediately from this description of the category Harish-Chandra bimodules for the torus, for the monoidal structure in terms of these shifts. And this is related to how Donin and Mudrov described dynamical R-matrices, except they have a slightly more complicated description in terms of so-called dynamical extensions of categories. Okay, and one example, which was the main watchmaking example, is to understand something called the standard rational dynamical R-matrix. So it's a dynamical R-matrix for the Lie algebra G, and this arises exactly from this parabolic restriction functor. So you start with Harish-Chandra bimodule for G restricted to Harish-Chandra bimodule for H. So you have to look at this generic subcategory. As I said, free modules are sent to free modules. So it satisfies this, this assumption. So it factorizes through subcategory of rep H. And the claim is that if you extract the corresponding dynamical R-matrix, that dynamical R-matrix is the standard rational dynamical R-matrix. You can repeat everything for quantum groups. So replace UG by UQG. There's a completely parallel story. What you get is the so-called standard trigonometric dynamical R-matrix. Okay. So I'm also out of time, but let me say a few words about the wild group action, something Richard asked. Okay, so in the Harish-Chandra homomorphism, we have the standard fact that it doesn't just land in SimH, it lands in W invariance in SimH. What's the analogous property for parabolic restriction? Well, let's look at again this symplectic explosion correspondence, G dual mod G, H dual mod H, and the bimodules B mod B. And then you can compose it with itself if you read it backwards. So you start with H dual mod H, go to G dual mod G, then go back again to H dual mod H. In this way, you get some Lagrangian correspondence from H dual mod H to H dual mod H. Okay, so what this is going to look like is it's going to be cotangent bundle of G mod n and quotient by H on both sides. Okay, and as you can imagine, this quantizes to D modules on G mod n, which are bimodromic for the H actions. And also on both sides, we have an action of the category Harish-Chandra bimodules for H. Okay, now we can use the Burchard decomposition of G mod n to extract the action of the actual wild group. It's going to be slightly weaker than the action of the wild group. It's going to be the action of the corresponding braid group, corresponding to the wild group. But okay, so the idea is that this bimodule category gives rise to a functor from HCH to HCH for any element of the wild group. And the claim is that if you look at this localization, so you throw away the weights, then this parabolic restriction functor is going to land in W invariance. And you get a monoidal functor from HCG into HCH W invariance. So you can think about that as being categorical version of the fact that Harish-Chandra homomorphism lands in W invariance. Now, if you think of what this means for for a free Harish-Chandra bimodule, well, this is going to give you some operators for any element of the while group, some endomorphisms of the representation, which are again parameterized by element of the carton. So it's the dynamical parameter. And the theorem we're working on right now is that in this way you get the so-called dynamical while group action, which was introduced by Engov, Tarasov, and Marchenko. And just a few quick comments. The category Harish-Chandra bimodules has a Langlands dual description in terms of D modules on the affine Grossmannian, which are G of O covariant. And there's a similar description of the dynamical while group action on the Langlands dual side given by Brauerman and Finkelberg. So in this case, they obtained this dynamical while group action using equivariance localization. And also there's some related work by Ginsburg and Risch, also obtaining dynamical while group action from a similar setup. Okay, so I'm gonna stop here. Thanks.
Okay, great. So people should be able to unmute themselves now. So if you have any questions, feel free to ask.
I have several questions, but they're kind of like very open-ended. I mean, do you understand at all the connection between this bimonodromic category and the recent category constructed by Achar, Makisumi, Risch-Williamson?
No, not really. I didn't.
It's like a Zirkel version of it.
Mm-hmm.
Well, the exact word you're talking about isn't popping into my head, but I mean, somehow like, right, a lot of that sort of Koshal duality, Zirkel style stuff, you're like fixing one central character, whereas this is sort of looking at all of them together.
That's exactly what Gerbier just texted me. Thanks.
So I feel like it's a very different flavor of work.
Understood. Thanks.
Well, as people are thinking about questions, I don't know, maybe you just addressed them all too well in the talk.
I apologize.
Oh.
Can I ask you one more question?
Yeah, of course.
Regarding to this going from Pavel to parabolic. So at the end you have this var group property. So in the parabolic version, in this time in the var group, what replaces the var group? Should it be the subgroup corresponding to the Levy subgroup?
Yeah. So we haven't looked at that yet, but indeed you would expect the corresponding while group related to the Levy, and this is exactly what. So you can look at the Harish-Chandra restriction not to the carton, but you can look at Harish-Chandra homomorphism into any Levy. So there's this exactly the way I've written it somewhere. So here H doesn't have to be the carton, H can be Levy, and W is the corresponding while group. And you would expect exactly the same statement on the categorical level, but we haven't looked into that yet.
I have maybe a comment about Ben's question and Ben's answer to it, other Ben. So yeah, I think that's right, that this is sort of different from this usual Zergel story in that you're not fixing a character for the cartoon. But when you look at it causal-dually, I think it's actually not that different. More precisely, I think this category of this sort of big-looking category of bimonodromic things on G mod n looks something like the equivariant affine Hecker category. So you have G of K mod I, strong I on the left and right, and then you basically invert the loop rotation parameter. So I really mean the Kac-Moody, the whole Kac-Moody group, G of O mod I. with the dupe rotation parameter inverted. And I think that'll look something like this bimodromic category. So it's some localization of something that looks a bit like usual Zergel bimodules.
In affine Zergel bimodules, you often end up with these monodromic complexes where d squared is not 0, but it's exactly this loop rotation element. So usually, if you usually instead of inverting it, you either kill it or allow yourself to have that kind of monodromy in your complex.